Hello everyone, my name is Konstantin Vladimirov and welcome to the fourth lecture of our master's course in modern C++. Today we are beginning something special, a lecture series that forms the very heart of the first semester. We have many fascinating topics ahead of us like ranges, models and so on. But to truly understand them, we need to build a solid foundation. We need a systematic way to think about the language. And that's what we'll start building today. We'll examine two fundamental mechanics, name lookup and overload resolution. By seeing how they work together, we'll naturally arrive at a powerful conceptual framework that I call semantic processes. Now, semantic processes isn't a standard term from the C++ standard, but I found it incredibly useful for untangling the language's deepest intricacies. And let's connect this to our last lecture. We discussed the two building blocks of generic programming. The first was generic classes, and the second was overload sets of generic functions, and we investigated the overload set for the nth power function. Uh, by the way, pay attention to an elegant point I didn't show last time. If I use std_integral outer x here, then to understand what type will be returned, I don't want to leave just outer. That would be a bad overload set if we allowed function bodies to influence their interfaces. So here I use the syntax with the arrow and decl type of x. And this may be a hint for your homework. In a way, you can think of this or any other overload set of generic functions as forming a single, more powerful generic function because they share a same name. We refer to all of them by one name, and if you refer to something by the same name, then for you it's likely the same entity, although in C++ this isn't entirely true. And we stopped at the point that having multiple overloaded names means we need to somehow associate the name with a specific entity in the language. That is, this is name, and this is one entity, and this is another one. Okay. And please, never underestimate the complexity behind simplicity in C++. Say we just write foo left paren as right paren. What is it? The name foo is a starting point, not a destination. Name lookup must first find everything that foo could be, and before we can choose, we must know what the choices are. So, pause the video now and think what is the complete set of possibilities that the compiler will consider for this line. What are all things you can imagine foo of s could actually be? 3, 2, 1. Okay, and your list might be longer than you thought. Let me show you an example. Let me show you an example in Godbolt. Yes, this is it. And see, this is struct foo, and this is field named x, and this is some default constructor and some static field, and constructor of one argument assigning this argument to this static field, and this is static field definition. And first test uses just foo of s in brackets, but what is this? And as you can see, this is the default constructor, but how can it be? Okay, it's simple. These brackets mean virtually nothing. We just define this s variable with type foo. And then we are promptly expecting s.x to be equal to 1, because this is default constructor. Now, single argument constructor can be called like this, foo of x, in some expression like delete of new of foo of x, and here we have x equal to, and we are setting x equal to here And this static variable s, after this, we are checking foo colon s equals 2. And now we have regular function, and this is regular function call, because if something can be function call, it is function call, and this is the case now. This wasn't the case here because this function was not in scope yet. And now this is function call. And we may check that this equals 3. And this is not the end. This list will be continued later in this lecture, but it is already fascinating enough, I believe. Okay, so let's see. It depends heavily, meaning of any name in the C++, depends heavily on what is around it. Looking at something in isolation, we understand not. We can only understand something by looking at the context above and below, and this is very important. Let's briefly recap the basics of programming language theory in a couple of slides so you understand what context dependence really is. I hope everyone has looked into the C standard since the start of the course. If not, please stop video now, go download the copy of the C++ language standard. And when you open this document, what do you see? And most often, you're greeted with this, a wall of formal syntax. This is the language grammar. I mean, the beginning of each language subsection. This one. Language grammar is the definitive rule book. Let's use unary expression as an example. This rule lists everything that can qualify as a unary expression. To make sense of it, you need to understand the notation. A big part of it is the typography. Notice that some terms are in italics, like postfix expression, while others are in bold, like size of. And this isn't just for style, it has a specific meaning. The bold words are terminal symbols. These are the actual keywords and operators or constants and so on you use in your code. The italicized terms are non-terminal symbols. They aren't used directly. Instead, they represent constructs that are defined by other grammar rules elsewhere. You need to follow these links to see what they expand into. We know what unary expression expand into, and now to understand what is postfix expression, you need to just follow link, look up the postfix expression grammar rule, and look up what postfix expression will expand into. And in essence, the bold text shows you the keywords and italics show you the structure, guiding you to other parts of the grammar for the full definition. And now let's look at the basic rules. And the general form of basic rule, A colon B, is called a grammar production. It simply means A can be replaced by B. Unary expression can be replaced by plus plus cast expression, minus minus cast expression, and so on. Remember the fonts, italics are non-terminals. They are temporary constructs that must disappear, and bold are terminals. And now a key point. I claim the C++ grammar is largely context-free. Why? Because every rule has a single non-terminal on the left-hand side. Like here, unary expression on the left-hand side, and some non-terminals, some terminals may appear only on the right-hand side. And on the left-hand side, you may check every grammatic rule in the standard, in the C++ language standard, and you will see on the left-hand side only single non-terminal. And this means a rule like if statement applies the same way everywhere in the code, regardless of its surroundings. An if is always an if 4 is always a 4. The context doesn't change the rule itself. This single property is what makes grammar relatively systematic and, what is important, easier to parse. And now let me ask you a slightly strange question. Look at this code. From a purely syntactic perspective, ignoring what it does, is this program correct? Does it contain any syntax errors? This program, I believe. It's actually quite hard to answer just by looking at it. We need something more formal, so let's consult our rulebook, the grammar, and find out. And we have unary expression, which includes delete expression, in turn includes cast expression, and cast expression includes unary expression. And thus delete p is perfectly normal syntactic construct. It passes parsing. A parse tree can be built in theory. What it doesn't pass is something else. And what is it? This is type checking. Type checking fails because delete returns void and the next delete requires a pointer. This is a problem with semantics, the meaning of the construct. An expression can be grammatically correct, but meaningless. It's the same way in any natural language. A phrase can be grammatically correct, but make no sense. And one problem of any grammar is ambiguities. A grammar with ambiguities was written for C++ as well. Consider this expression, delete, square brackets, return new int, and now function call. What have we done? Maybe, just maybe, we created a lambda function that allocates memory, then we called it, and then immediately freed the memory using delete. Correct? Let's check grammatically. Delete expression is delete cast expression, and cast expression is unary expression, and blah blah blah, and lambda expression here. So syntactically it is possible. Nevertheless, there will be a compilation error here. Why do you think? And this is because the standard have not only the grammatic rules, also the standard have human readable text. And in this human readable text, the standard implicitly states whenever the delete keyword is immediately followed by empty square brackets, it shall be interpreted as the second alternative, as delete square brackets alternative. And so you will get this error because this everywhere delete square brackets and this is random gibberish. And in semantics, why questions are all very difficult. Why this is done this way? Most of the time, the answer is for historical reasons. What I mean is when we look at C++, many rules in the standard were chosen from equally valid options simply because a decision had to be made. There's no logic. You just have to read the document. And the language contains context-dependent constructs. For example, the meaning of square brackets is determined by what comes before and after them. And this is a fundamental property of C++. So a natural question arises, why is a context-free grammar then used for our language? If the language is context-sensitive, wouldn't that be a mismatch? And the answer lies in the algorithmic complexity and the separation of concerns. And let's play my favorite game, guess the complexity. We know that parsing a context-free grammar in the worst case is proportional to the cube of n. And now what about parsing a context-sensitive grammar? Please vote in the comments of this video. Do you think it's simpler that like 10th power of n? Or maybe you think it at least polynomial? Or maybe you think it is NP-hard problem? Or maybe you think it is p-space hard problem, or maybe you think this is x-time hard problem. I will not spoiler the answer here, but you can guess that the real complexity is really hard. And this is interactably hard for compiler that needs to process millions of lines of code. And therefore, we use a crucial design principle. We separate the process. We first use a context-free grammar to build a parse tree handling the basic syntactic structure efficiently, and then a separate, more powerful semantic analyzer takes over to resolve all the context-sensitive questions like what do the square brackets mean in this specific context. Semantic is about meaning. The parser works together with the semantic analyzer because it will be ineffective to build the whole tree in prior. And what is actually happening inside Clang? The parser says, I want to parse a deleted expression. Can I add it as a new node to the tree? And the analyzer checks the context and says yes or no. So, do we need to teach people semantics? From my point of view, the answer is resounding yes. Why? Because when a person reads a C++ program, they are acting as an abstract execution machine. They are mentally modeling the language's behavior. Of course, one might argue that the compiler can help. We can just compile the program and compiler will tell us if it is correct or not. Let me show you how the compiler will help you. Okay, let's see. This is GCC trunk and this is Clang trunk, the latest and the greatest version of both compilers. What GCC do? It crashes into internal compiler error. What Clang do? It crashes into internal compiler error. And I presented this example at a conference 3 years ago. And here is the key point. This hasn't changed. To this day, when faced with this code, they don't tell you the program is incorrect. They simply crash. And now look at this code. The issue is that I forgot constexpr on foo. And for human, it is obvious. But the compiler doesn't diagnose that. It fails catastrophically. So who will help you then? And no one will help you. You, the human, must treat it yourself and deduce, oops, this function must be constexpr to be used here. And if the code is written correctly, both compilers handle it without any issues. This is a perfect example of why we cannot rely solely on the compiler. We must teach semantics to people so they can understand the code when the tools themselves fail. Okay. And we see that semantics is present around name resolution as well. Maybe not only there, but how will this help us with generic programming and our main building block, overload resolution? In this lecture, we will examine overload resolution rules from start to finish with examples. And here is a high-level overview of the overload resolution rules. The process follows the steps. And this slide will be repeated once again, and any new repetition of this slide, this blue highlight will go down, down, down until it will come here and lecture will be over. Okay, so first the set of overloaded names is selected. And now let's pay close attention to the journey from the first to the second bullet point here. We will spend the majority of this lecture, roughly half of the time, analyzing this specific step. the path from selecting the set of overloaded names to selecting the candidate set is the most complex and nuanced part of the entire process. And it's absolutely crucial to understand because this is where name lookup happens. Okay, and now the compiler, when it sees a name, has a seemingly simple task to collect all entities that could theoretically correspond to it. It seems like a 5-minute job, right? Okay, now back to the question of whether we need to teach semantics. Someone might argue that we don't, because we can always ask large language model like ChatGPT, our modern oracle. 3 years ago, ChatGPT failed on problems like this. Let's see how it fares now. Here is the problem. We have a function foo and struct foo with a constructor. They can coexist. The question is what happens for foo of 0 and foo curly brace 0 curly brace. Is it the function, the constructor, or an error? And yesterday I asked ChatGPT and its final answer was this is a compile time error and this unambiguously calls the struct constructor. It provided a detailed step-by-step explanation and even quoted the standard to justify its reasoning. So, who here has a different opinion? Think a little. 3, 2, 1. Okay, in reality, according to the language standard, the truth is exactly the opposite. ChatGPT didn't guess a single line correctly. This is not an error, it's a function call, and this is not the constructor, it's an error. But look at this strange error message. Expected, I believe, semicolon before curly brace. What is it talking about? What name did the compiler actually find here? And the key is that for full curly brace, 0 curly brace, name lookup find both the function and struct. But the context of list initialization is ambiguous. We are trying to create an object or we are dealing with the function. And the standard has a very specific rule to break this tie. Since foo can be interpreted as a function name, the compiler first tries to parse foo as a function, and from that point of view, foo looks like either function body trying to start or even a discarded function pointer. The compiler considered the function, found the syntax invalid for it, and gave up. It never even got to the stage of considering struct foo as its constructor for this initialization. And so we have names that can coexist and names that can be overloaded. You cannot overload structs, enums, namespaces, or variables, and mentioning a namespace with the same name simply reopens it. And this graph shows name incompatibility. You can have function and struct with the same name in, say, in global namespace or in any namespace because there is no edge here. But you cannot have function and namespace with the same name or namespace and enum and so on. Okay, so we now know which names can coexist. Now let's ask, when we have multiple declarations, what does the compiler consider to be the same entity and what does it see as a different overloadable one? This breaks down into two main categories. The first category is when overloading is outright prohibited. The compiler sees two different entities trying to use the same name and immediately throws an error. A classic example is two functions that differ only in their return type. The second, more subtle category is when what looks like a different declaration is actually treated as a redeclaration of the same entity. The compiler doesn't see an overload, it just sees you repeating yourself. This happens, for instance, with a top-level const on a by-value parameter. The underlying logic here is all about name mangling, but I will not dive deep into detail. I will show you an example instead, because it is much more interesting. So let's us look into this great Godbolt example. And this is what is redeclaration. Redeclaration is declaration with type def. Redeclaration is declaration with const on by-value parameter. Redeclaration is declaration with another set of default parameters. And what is other entity? What is non-overloadable entity? First, it is this one. Overload on no except is prohibited. Overload on return value is prohibited. Overload static versus non-static function in struct scope is prohibited, and overload ref function versus non-ref function inside struct scope is also prohibited. Now we are talking about names. We can see non-overloadable names, indistinguishable names. What other names? And a question for beginners. 0, as we see here, 0 is more likely to be int than a const char pointer, because this is 0. This is not a null pointer. Think a bit. Pause the video. What could be here? Actually. 3, 2, 1. Okay, of course, answer is 2. The function f inside struct d hides, this is hidden name, hides function f from struct b. As a result, we simply don't look for f from b. This name is hidden in another scope. And next question for intermediate level, minimal changes to get 1. 3, 2, 1, of course, using b : f. This introduces name into scope. Perfect. In this case, the name was hidden in the scope of the parent class, but now it is visible in the scope of the derived class. Great, but what are scopes? What kind of scopes do we have in C++? We have like namespace scope, template parameter scope, class scope, function parameter scope. Of course, we do have a block scope, and we mustn't forget the often overlooked enum scope. We will not meet this scope in these lectures again. Now, here's the critical point. These scopes are not created equal. Their rules vary greatly, and this is a common source of surprises. The slide shows a perfect example. A double using declaration bringing the same name into the same scope twice. Inside a namespace, that's perfectly fine, but in the block scope, it is an error. A double declaration. This illustrates how scopes have a kind of hierarchy or size. Block scope is one of the most restrictive, the smallest in terms of what it allows, and the namespace scope is much more permissive. Understanding these differences is essential for predicting how name lookup will behave in different parts of your code. And we've seen how scopes and declaration rules affect lookup. But this is not all. There's another, more subtle factor at play. Look at this setup. This is one of my favorite setups. We have two namespaces, B and C, each with its own variable x. Now, inside namespace A, things gets interesting. We have a using directive for namespace B which makes all names from B visible. And then inside the function f, we have a using declaration specifically for C::x. This creates a fascinating situation. We have two different ways of bringing the name x into scope. So here's the puzzle. In the line a::x equals 1, which x are we referring to? This is this. And then on the very next line, we write x equals 2. Is this the same x as in the previous line or a different one? Pause the video now, think about it. Read the standard. Could a::x and the plain x right next to it inside the same function possibly refer to different variables? The answer is more surprising than you might think. And let's break it down. The K is the difference between qualified and unqualified names. Using C::x is a declaration. It injects the name x from namespace C directly into the current scope, the block scope of f, and it acts as a local synonym for C::x. So an unqualified x inside f will find this local declaration first and refer to C::x. And using namespace B is a directive. It does not declare any names in the current scope. Instead, it makes the names from B visible as if they were in the nearest common ancestor namespace. For a qualified name like a::x, the compiler will look inside A and find the x that became visible from B via the directive. To truly master name lookup, we need a precise vocabulary for the different kinds of names we write. Let's build a systematization from the ground up. At the most basic level, we have an identifier. This is a simple sequence of letters, digits, and underscores like X, F, or MIR. Now, when we use a template, its name is also just an identifier, but when we provide arguments like MIR angle bracket T, 1 angle bracket, it becomes a template ID. To group these concepts, we have unqualified ID. This is a generalization of an identifier that also includes more complex names like operators, like destructors, like user-defined literals. And when we add scope resolution, we have a qualified ID like std::out, foo, : destructor foo, and so on. This is any name preceded by : Here, foo preceded by : like destructor of foo preceded by : is qualified, and foo itself is unqualified. It is qualificator, but it is unqualified itself. And here, std is itself qualified. And now for the crucial part of lookup, we often talk about the terminal name. This is the final lexical name that the lookup process is ultimately searching for. In this arrow F is the terminal name. And finally, an unqualified name is simply a name used without any preceding : dot, or arrow. This arrow F, name F, is qualified. This is not qualified. Understanding these terms, identifier, template ID, qualified ID, and especially terminal name, is the key to deciphering the standards rules and predicting the compiler's behavior. And the general rule for name lookup is somewhat intricate. In any scope, a simple search is performed first, then base class lookup, then unqualified lookup. Then, if necessary, unqualified lookup is repeated as argument-dependent lookup. If the name is qualified, qualified lookup is performed by unqualified lookup is part of it. This order was explicitly written down only in C++23. In earlier standards, good luck to guess. Let's start with the most basic mechanism, simple lookup or single search. The definition is straightforward. A simple lookup in a scope S for name n finds all declarations of n in that scope. But, as we'll see, even this simple lookup has immediate consequences. The example on the slide shows why. We have a namespace n and a local variable n. N, and here is n. And namespace n can coexist with local variable n. It can coexist with global, but local variable isn't in another scope. And now look at this line, and this is okay. But how does this work? The first n in n plus equals something is found by simple lookup in the local scope and finds the variable n, and that's it. But n colon colon x is a qualified name x. The part before qualification is looked up separately. The crucial point is that lookup for a name used as qualification ignores non-namespace entities. Since the variable n is not a namespace, it's ignored for this specific lookup. And this leads to a critical observation. When you hide a name, you only hide it for lookups that don't explicitly ignore that kind of entity. And base lookup is more complex. It collects the set of names from the class scope and all its base classes and then searches within the set. Now we come to a complex area. Lookup in base classes. This is the process that happens when we use an unqualified name inside a class or class template like X. X is unqualified name. The key idea is that the compiler doesn't just look at base classes individually. It builds what the standard calls a set of sub-objects. This S is set of sub-objects. This set combines declarations from all possibly virtual base classes of the current class. And let's look at our example in class C, which inherits from A and B. Here it is. When we look for the name X, the compiler builds the set S. It finds X in A and X in B. Both are valid findings, so this set contains both declarations. This creates an ambiguity that makes the program ill-formed. But here the subtle part. Even when lookup succeeds in finding a unique declaration, its use might still be erroneous. Look at the struct E. It inherits from both A and D, but D itself inherits from A. Through both paths, we ultimately find the same X from the original A, so technically, lookup finds the same final declaration. However, the path to get there is ambiguous. The compiler doesn't know whether to go through A directly or through D to reach the same X. This is why it's also an error. This shows that base class lookup has two layers. First, gathering all potential declarations into the set S, and then applying additional rules to determine if the found result is actually usable. And now it's time for my favorite lookup exercise, one that perfectly captures the tension between different name lookup rules. Let's walk through it briefly. We have a template struct B that inherits from A. Inside B, the function f uses the name t, but here's the crucial ambiguity. T could be the struct T defined in the base class A, Or it could be the template parameter t. Here it is. If t refers to the template parameter, then t creates object of type s and x equals 2. Otherwise, x equals 1. So pause the video now. Think carefully. Which set of rules applies here? Does the template parameter hide the base class member? Or does the inheritance change the game? Try to reason it through before we continue. By the way, ChatGPT answers that here will be runtime error. And when I explicitly reminded that S has a member X, ChatGPT answers that valid answer is 2. It was also yesterday. So do you believe ChatGPT? Do you believe ChatGPT? As I believe it. By the way, I also asked DeepSeek, and DeepSeek agreed with ChatGPT. And I even said DeepSeek, ChatGPT here thinks 2. And I expected DeepSeek will answer 1, just for the sake of discussion. Okay, I hope you had your chance to look into the standard, and the correct answer is, of course, 1. This is slightly goes against intuition that a template parameter would hide the base class name, but let me explain the precise sequence the lookup follows. When it sees name t inside a b colon colon f, it performs unqualified name lookup. It starts in the innermost scope, the function body, and finds nothing, and it moves to the next enclosing scope, the class b itself. And when lookup happens in a class, it immediately searches the base classes as a part of a single unified process for that class scope. This is the key rule we often forget. So in the scope of B, the lookup for T searches the base class A and finds A colon colon T. It finds a declaration and stops. The search is successful. The template parameter scope is never even considered. This teaches us a vital lesson. Name lookup in a class scope is a special combined operation that includes its base classes before moving to outer scopes like template parameter scopes. This is why, do you recall the scope hierarchy? Here how it plays. This is why understanding the exact order of operation in non-negotiable. Okay, and now we arrive at the central concept of this lecture, which I believe can help us untangle the rest of the language. Did you see how I just explained the previous example? I walked you through it from the bottom up. I started inside the function f, and this t, and what can it be, and so on, so on, so on. That's how a human reasons about code. We mentally execute a process of searching and deduction. But the compiler doesn't work that way. It parses the code top down, line by line, progressively building and updating its internal symbol tables, like this blue arrow. It's not searching in a human sense. It consulting structure that are already in place. And this fundamental disconnect is why I want to introduce the special notion of a semantic process. A semantic process, as I said, is not a standard term you'll find in the literature. It's a conceptual framework I offer it to you. From my point of view, it's incredibly useful tool for thinking about the most complex parts of the language. Believe me, I'm lead of tools team. A semantic process is the logical procedure that a human must actively execute in their mind to understand the meaning of a code construct. And name lookup is just the first of these processes we are meeting. In the coming lectures, we will see others like template argument deduction and overload resolution and template instantiation and so on and so forth. Now a word of advice. If your coder forces you to painfully trace these processes in your head, it might be a sign to simplify it. But your goal as a C++ developer will be better served if you learn to recognize and run these processes when you need to. It transforms the language from a collection of rules into a predictable logical system. And for qualified lookup, there is a special rule for using namespace. If namespace B is nested in A, the names from B appear as if they were declared in the greatest common scope between the using directive and the target namespace. And in this case, like they appear in the global scope. So, okay, this is C : X. And during unqualified name lookup, uh, the name appears in the most common scope. So here we will have error because we found both. And now let's tackle qualified lookup. The rule on the slide is correct but needs careful interpretation. Qualified lookup does perform a specific kind of search in base classes, but the key insight is that it follows its own strict hierarchy. First, it looks for explicitly declared members in the specified scope. Only if it doesn't find anything there, it looks at names made visible through using namespace directives. And the crucial difference from unqualified lookup is this strict priority. Explicit declarations always win over using namespaces in qualified lookup. And of course, qualified lookup doesn't ignore using namespaces. It just gives it lower priority than explicit declarations in the search order. And qualified lookup good for its stability. For a name to be found by qualified lookup in most cases, it must be explicitly introduced into the specified namespace. This will always find set C : X, and this also will find C : X. We may play around it. We may place this namespace here or there or everywhere. If you explicitly introduced something in the scope of qualification, qualified lookup will find specifically introduced name. Then it will go and analyze using namespace and so on and so forth. And now we come to non-obvious problem. What to do? What do we do with operators? We know that an operator like left shift can be defined in any namespace. The expression stud count output hello is essentially equivalent to calling a function operator left shift stud count hello, studs out hello. And I believe operator left shift is a really unlucky one. But for this to work, that function must be found in the stud namespace. So what we really need to call is stud operator left shift studs out hello. And here lies the problem. Look at the syntax studs out hello. Look at this syntax. From this notation, the compiler has no way of knowing that the operator left shift should also be looked up in the stud namespace. The stud qualifier only applies to the left-hand operand cout. This issue was discovered very early on when the EOStreams library was first being developed. So, pause the video now once again, and how do you think in the C++ language, how do you think the C++ language designers solved this? Now, how can we tell the compiler to also look for the operator in the namespace of one of its arguments? Try to figure out the solution before moving on. 3, 2, 1. Okay. The solution proposed by Andrew Koenig in the early 19th is what we now call argument-dependent lookup or Koenig lookup. The rule is elegant. After the compiler performs an unqualified lookup and doesn't find the name, it performs a second lookup. And this time, it looks for the function name in the namespaces associated with types of its arguments. Let's look at an example. In the call f of a, the variable a has type n colon colon a pointer. Unqualified lookup for f finds nothing in the current scope, but then ADL kicks in. It sees that the argument type a comes from namespace n, so it goes and looks in namespace n where it finds n colon colon f. This is exactly how operators work. In our std left shift hello example, ADL sees that the left-hand argument std is of a type defined in the std namespace, so it automatically looks in the std namespace for a suitable operator for left bit shift and finds it correctly overloaded. This is the magic that makes stream output work seamlessly. However, Koenig lookup has a subtle but important fragility. ADL is only triggered if unqualified lookup finds nothing. If unqualified lookup finds any other kind of entity, like a type, a variable, a template, then ADL is completely disabled. Look at this example. We have a global type def of f. Now in the call f of a, unqualified lookup immediately finds this f. The search stops here. Since it didn't find a function, ADL is never even attempted. The compiler then interprets f of a as a functional style typecast, trying to convert a to type f, which is int and which is perfectly normal. This will, of course, not what we expected. But the key point is that the function n colon colon f was never considered. This is why the interaction between regular unqualified lookup and ADL can sometimes lead to surprising results, where a function you expect to be found is completely invisible to the compiler. And now let's look how Koenig lookup interacts with templates. Consider this example. We have a function template, I believe, f in the namespace n. And we try to call it explicitly. And this fails. And it fails with a truly cryptic error message, something like expected primary expression before int. And this is a classic head scratcher. Everything seems like it should work. We have the template in namespace n. We have an argument of type n colon colon a pointer. So why doesn't ADL find it, and why is the error so completely unhelpful? And to understand what's going on, think about the parsing stages. What does the compiler think when we are trying to do when it sees f angle bracket int angle bracket a? What compiler can think in here? And wow, compiler thinks it is a operator less. And if no matter what signature of template will be introduced here, if this name will be introduced here as a template ID, recall our name classification in the beginning of the lecture, then everything will be good. The signature don't matter. And on this slide, we have perhaps one of the best examples of why unqualified names can have a dangerous reputation. Look at this code. It outputs on the screen hello world, not hello hello. But why? We have a namespace A that mischievously defines its own struct stud, which is perfectly fine. We do have namespace stud, but in other scope. Struct stud is fine struct with a members out, which is also fine. And it even defines an operator of logical bit shift for it. Now, in main, we have using stud to introduce this name into main. And now, if we are using unqualified stud, we are immediately finding this one, which is this one, which outputs world in any cases. And this stud shout hello uses a qualified name. And this stud explicitly refers to the namespace stud in the global scope. And this is why the standard library always uses the qualified stud : prefix. They cannot rely on unqualified lookup because it can be hijacked by this by local declarations. The lesson is clear. If you want to be absolutely sure which entity you're using, always prefer qualified names. And there is also a funny exception to ADL: hidden friends. Friend functions declared inside the class are only found via ADL. This is a powerful technique. If you declare the equal operator inside a class as a hidden friend, it will only be found for objects of that type, not for types convertible to it. And this helps avoid unwanted implicit conversions, like this will work and this for derived classes will fail. And of course, if this will not be friend in the scope of X, if this will be like free function, then this will pass. And on YouTube, there is a whole video on hidden friends and how to use them. And now we have reached the second point of overload resolution: selecting candidates. As I promised, we spent a lot of time on the first point. Now we need to select the candidates, and note, immediately after overload resolution, the next process starts: type deduction and then template instantiation. So when overload resolution will be over, here we'll start like type deduction. And during the candidate patching process, type deduction and instantiation can already be triggered inside the overload resolution process. Say we call function bar of u instantiated, and this bar is candidate, but it is a bad one. And there is no conversion to S here. And then the compiler will find any name bar, try to deduce the type, instantiate the template, and only then understand that the candidate is unsuitable. And so we can see that semantic processes can chain into each other. And the third point is viability. What is viability? Viability for overloading is primarily about matching the number of parameters. Here we are making this call with two parameters, and we pass one, the candidate is not viable, accessibility, private functions are not viable, and explicit constructors are also considered. So this is viable because it can be code with two parameters. This is viable because it have default parameter, and this is definitely not viable. And you can see or even pause the video and read extensive quote from the C++ language standard here. And after this, the best candidate is selected based on the chains of implicit conversion for each parameter. And this one is interesting. From a naive perspective, the conversion chain includes with highest priority standard conversion, with slightly lower priority user-defined conversion, and with lowest priority ellipses. But complexities arise when many different ones are combined. Obviously, here, when we are calling foo of 1, we want to call foo of int. If we remove it, foo of s will be called because the user-defined conversion from int to s exists due to a constructor with one parameter. And if we remove 1 and 2, then ellipsis wins. But the standard conversions themselves have many ranks. If we trying to call foo of int or foo of char, foo of int wins. Foo of char and foo of double wins, because standard conversions are not created the same. Standard conversions have ranks, and ranks used in the overloading. There are 3 ranks: exact match, promotion, and conversion. Exact match includes, for example, L value to R value, array to pointer decaying, function to pointer decaying, qualification conversion, promotion, for example, integral promotion, and conversion, for example, floating integral conversion. So exact match is in some sense requires no work from compiler. Promotions and conversions require some work. So if we are looking here, this is array to pointer conversion. We have P, we have R. R may be treated as pointer to its first element. Qualifier adjustments. This is constant qualifier adjustment. This is int pointer, this constant pointer. Promotion, like int result is true, and conversion, like float f equals 1. And user-defined conversions look like this. In struct A, we can define either constructor from int or operator int that converts A to int implicitly. You do have both operator int and operator double operators, and we are calling like this. We're just constructing A and implicitly converts it to something. Here, 1 is better than 2, and this is really non-obvious. From naive point of view, overload resolution do not consider left-hand side. It happens on the right-hand side only, but here we do, because we can have a head of standard conversion, then user-defined conversion, and then a tail of standard conversions. And if we will look this way, what do we have here? Here we have zero length head. We have no standard conversions. Then we have one user-defined conversion in 2 ways, to int or to double. And then either no implicit conversions or one double to int implicit conversion. We have tail that longer if double wins. So int wins. So if we are building implicit conversion sequence, ICS, we are building this chain to analyze its tail. And you may ask, what can we do if we have two user-defined conversions? Like, what will be a tail of one, a tail of two, and so on? And the C++ language standard answers simply, you cannot. You just cannot have two or more user-defined conversions in the ICS. Like in this example, in this case, we have x of type int, and we are calling for foo of x, and x is converted to long, and long is converted to s, and foo is called. And here looks like this is the same. Here we might convert 42 to t, t to s, and call the function int to long to s or int to t to s. Why t is worse than long? Because it is user-defined conversion. And you just remember, only one user-defined conversion is allowed in the implicit conversion sequence. And the last bullet, if a best candidate exists and is unique, the overload resolution succeeds. Otherwise, the program is ill-formed. If no candidate exists, the program is ill-formed. But if overload resolution not succeeds because of two equally good candidates exist, the program is still ill-formed and diagnosable, because there must be no ambiguity in your overload set. And if we will return to the name lookup, it is really important where name lookup resides, because name lookup occurs before other steps of overload resolution. But name lookup occurs after alias substitution. And this is a very interesting case. Aliases do not participate in ADL. They are substituted away before the lookup process even begins. Here, we have using vector equals stud vector of int and a call to foo of vector here, and we might hope that this is ideal case. But the alias vector is immediately substituted for its underlying type with stud vector of int. The call effectively becomes foo of stud vector of int, and now ADL kicks in and only looks in the stud namespace for foo and finds nothing. This is why it's an error. This early death of aliases is why they have a somewhat better reputation in template metaprogramming. We will see this again when we discuss void t and sphere. Pause the video now, and given this rule, how could you fix this code? How can you make ADL work for a type defined in your own namespace? And here is the solution. Since the problem is that the alias vector disappears too early, the fix is to use something that doesn't disappear, a real user-defined type. Instead of type alias, we define an actual struct called vector inside namespace s. This struct can contain a stud vector of int as a member, but crucially it is its own unique type. And now when we call foo of s colon vector, the story is completely different. The compiler performs name lookup for foo and finds our function s colon foo. And it also performs ADL. This contrast is exactly what gives aliases their bad reputation. in advanced C++. They are transparent. They vanish during compilation. Sometimes that's what you want, but when you need a strong identity for a type, especially for ADL or for template metaprogramming, you need a real struct or class. Let's summarize. We have considered so far 3 semantic processes. Alias substitution, which in its own is semantic process, it's not grammatic. Name lookup and overload resolution. I combine them into one big process, which I slightly artificially call name resolution. And this is only the beginning of our journey. Who can tell me what are the major semantic processes await us? And correct answer is type deduction and template instantiation. In this lecture, I mentioned them both several times already. Moreover, all these processes can cycle. Imagine we have an overload set of template functions, min, and here is min of 3 arguments. It's okay. And we call min of 1, 2, 3. Name resolution occurs, a candidate is found, only viable candidate is this one with 3 arguments, and type deduction is triggered. Type deduction deduces this to be int, and then we are analyzing the body, and here after instantiation, name resolution happens again. Now we need to decide what this min is. And metaprogramming with template, as we will see later, is built on this cycle. I call this the wheel of samsara of semantic processes, or the normal semantic process. If you have name resolution, then type deduction, then template instantiation in your program, and then again, and it's over somewhere, you did a great job. It's a great program, very easy to understand. If you have something more complex than normal semantic process, and in the next lecture on type deduction, we will see how can we do something really more complex than this process. Then I believe that you are doomed. And next time we will look at one of its spokes of this wheel, type deduction. Okay, now homework assignment. The first, to understand an example, not necessarily type it into botbolt, use the standard manually, or maybe use ChatGPT if you believe ChatGPT. And if ChatGPT lists points from the standard, will you believe it then? An interesting possible research would be to train a neural network that deeply understands the C++ standard and answers such questions flawlessly. If you do know such a network, please send it to me. You may find my email on the first slide. The second task is also about knowing the standard, about those operators, operator bar and operator bus, differing only by const. An interesting task to dig into the standard. No coding tasks this time. Some bibliography. The first 4 items here are out of respect. Next, I again recommend you great talk of Titus Winters. His rule, a good overload set should not force a person to perform overload resolution in their head. And now I believe you understand why this rule is important. I also recommend Simon Brandt, Overloading the Bane of All Higher Order Functions, and Ansel Shermersheim, Back to the Basics Overload Resolution. They call their talks Back to Basics. I'm not sure what I just talked about, well, basics. And finally, Mateusz Push, back to basics, name lookup and overload resolution in C++, it's also great. So total about like 7.5 an hour of viewing to form like a stereoscopic perception. Forming a stereoscopic perception is not a synonym for going crazy, by the way. And next type, we have the good part. Next time, we will talk about type data. That's all for today. Thank you, everyone.